Welcome back, everyone, to our second inspiration hour. Um, Today we have a very special speaker, Shoko Sakai, and she's going to be talking to you about astronomy, specifically exploring the galaxies. So, to give a little bit of background about Shoko Sakai, um, Dr. Shoko Sakai received her bachelor's in physics from Cornell University and her PhD in physics and astronomy from Dartmouth College. She's been a research astronomer at UCLA since 2000, and she's been focusing on several distance indicators and understanding their systematics. More recently, she's been working on the supermassive black hole at the center of our Milky Way Galaxy at the Galactic Center Group at UCLA. So with that, I'll hand it over to you, Ms. Shiko Sakai, and you can take it away.
Thank you, Alexis, for a nice introduction. Let me share my screen. Okay, where did it go? Sorry. All right. Okay, can everyone see?
Yes, you're all good.
Okay, great. All right. Let's see. So thank you for inviting me to talk at your camp or online camp, whatever it's called. So today I thought, I know the title that Alexis gave was Exploring Galaxies, but I thought I'd give you a little bit background, or that my talk is titled Bigger Eyes to See More of the Universe. And I wonder what you might be wondering, what do you mean by bigger eyes to see more of the universe? So I thought I'd talk about the research that we've been doing here at UCLA, and also talk about the telescopes, which is basically the tools astronomers use to look at the universe, right? The objects in the universe. And then maybe in between, I would like to, I can tell you how I became an astronomer, or how I got to be interested in astronomy, that sort of thing. So just to introduce myself, I am an astronomer at UCLA. As Alexis said, and I have worked on various astronomy and cosmology topics, but more recently, let's say like last 5-6 years, I have been working on the supermassive black hole at the center of our Milky Way Galaxy. Okay, so we live in this galaxy called Milky Way Galaxy, and at the center of our own galaxy, there is a supermassive black hole, and we look at basically try to characterize that black hole and what's going on in the area immediately surrounding the black hole. Okay, so let's see what we have next. Oops. All right, so I live in Los Angeles, and if you look up the sky in the evening, that's what it looks like. Basically, you don't see much at all. So I don't really know where you're all from, if anywhere you're from LA, but this is Griffith Observatory right here on the right. It's right in the center of the city, and it has one of the best, evening, the view of the whole city. I live somewhere right around here, I think, if I can figure out where I live. But anyway, so, this is what it looks like at night. You have few stars. Maybe if the moon is up, maybe you can see the moon, and the handful of brightest stars. Maybe you might see more airplanes than, stars up in the sky, right? And I grew up in Tokyo, Japan, which was like this. It probably was worse than LA in terms of night sky. I really couldn't see anything much at all. But I got interested in astronomy because my parents took me to a planetarium. That was the only way really to see stars for me, other than going some very remote area where it's very dark and you can actually start seeing lots of stars, thousands of millions of stars. So I think I was about 8 or 9 when I first got introduced to planetarium, and I just got hooked. And I didn't really get serious about becoming really an astronomer probably until when I was in college. But definitely science, astronomy in general was something I loved pursuing whenever there was like the independent study or the project you had to do. I think in Japan, the school year goes from April to March. So summer is not really a break. We get tons of homework during the summer break vacation. And one of them that every kid has to do in Japan during summer is you have to come up with like some independent research, and you have to carry it through or do something, starting grade, first grade. And I remember it was always some astronomy subject that I picked just naturally. Anyway, so I got hooked to astronomy, and eventually I became an astronomer. So long, it took a while. So let's see. So this is just the sky that it looks like. The sky, I don't know, it's probably taken from some national park with very little light coming from the cities and towns nearby. So if this is, of course, your eyes might not see this. This is probably a long exposure, some photography, but you start seeing millions and millions of stars up in the sky. Yeah. So astronomy is one of the oldest sciences, really. But there's still although it's been around so long, there's still so much we don't know about the universe. Some of the biggest unsolved questions in astronomy are, let's see, how did the universe even start? Some of you might have heard the term Big Bang, how universe actually started from tiny little thing, and it's been expanding ever since. But to this days, we really don't have any physics to describe what was really going on in the very first, let's say, split second of the universe, right? What's going on? I'll be talking about black holes a little bit more later, but even inside black hole, there's no physics to describe what's going on right now. And then perhaps the biggest question that many of you might have asked or still asking is, are we alone? Or are there anybody out there? That question, right? Are there aliens out there? And I think this is kind of the ultimate questions, right? Are there anybody out there? Most of us think, well, there are so many stars you can see in the dark sky. There are millions of stars. Even if it's like 1% of those stars have planets, and maybe some of those planets are just like Earth, there's got to be somebody out there just like us, right? That's like the ultimate question for us. Now, whether we're going to meet those guys or not, that's another question. Maybe that's not the astronomy question. That's more like a political or a sociological question. But, for us astronomers, basically, are there anybody out there? And also, closely related to that, when we want to ask, are there anybody out there, is really asking how we got here. How did Earth get here, and how did we get here? That's really the ultimate question. So I think doing astronomy really is like every one of us has like a little tiny piece of puzzle of the universe, and which we're trying to solve. And then when we put a lot of those puzzles together, we start seeing how the universe works and the whole history of the universe, how it has evolved last 14 billion years, and where we're going to go from here. Okay, so, and then of course, what do we use to figure those things out? It's basically, we use a telescopes, multiple telescopes. And the basic idea has not changed since the Galileo days. Okay, so Galileo, actually, he did not invent telescopes. It was Hans Lippershey or somebody in 1608. He's the one who actually invented telescope. But Galileo heard about the thing called telescopes, and he was the first one to actually look at the sky with the telescope. And go to the next one. Those are actual drawings done by Galileo. Here it's one of the sun on the left. Okay, those are if you don't look at the sun, but I'm sure you heard that so many times, don't look at the sun directly, or don't ever look at the sun with a telescope or binoculars or anything, because you can damage your eyes. But if you look at the sun, you see the sun is not just this like a smooth yellow object. There's some darker spots on it. And then Galileo actually was able to observe that for the first time. Here are those sketches made by Galileo of Mars, right? There's a dark side and bright side of the Mars, just like this moon. We get the dark side of we have phases of the moon. He saw that, and the details that he was. So it's quite amazing, and it's just like 400 years ago. Oops. Oh, wait, where did it go? I clicked something wrong, and then it went somewhere else. What happened?
Not like that's ever happened since we've been here.
What is that? I'm gonna quit something so I don't get confused.
Yeah, you pick up in the middle there a little.
Yeah, let me share it again. Okay. All right, here you go.
Yay.
Right. So let me just tell you very briefly that what the purpose of telescopes, what the purpose of telescopes is. Okay. And then, I think that you know the purpose of telescope, just to see something really tiny and faint, right? Like we're trying to see some galaxies, stars, planets that you just cannot see with our own eyes. Even the Galileo's telescopes are very primitive for what we have today. You know, you can go into Walmart and get a telescope that's 1,000 times better than what Galileo had. But you could see, even with that really simple telescope, basically it's just a tube with a lens in front, a lens in the back, and then it magnifies what you're looking at, right? So, but even with just a simple telescope, he was able to see the details on the surface of Mars and so on. Okay, so astronomers have been kind of driven to make larger telescopes ever since. And why do we really want those larger telescopes? So let me tell you, right? So what is a telescope? What is the purpose of telescopes? It's basically light collecting buckets, right? That's what they are. And if you think about something raining down, and you want your job is to collect as much rainwater as possible, right? And what do? You want the little small bucket, or do you want the bucket with a very large mouth? And obviously, most of you are going to pick this one on the right, because in the same amount of time, right? If you're allowed to put those bucket for 1 hour during rain while it's raining, you know the one with a larger surface area at the top, right? With a bigger mouth will collect more rainwater in exactly same amount of time. Exactly same theory with the telescopes. The larger the area of the telescope is, the more light it can collect. And that's the light that's coming from really, really far, the galaxies and stars that's coming from really far away. So you want to make sure you collect every little light, every tiny amount of light, as much light as possible in a given amount of time that you're able to observe that object. The other thing is that if you look at this picture, it's not a very high resolution picture here, but there's some of this jargon, angular separation that you see here. But if you're standing on the road, in the middle of the road, which I don't suggest you do, but if you see a car that's coming from really far away, when the car is very far away, you might see those two headlights, right, of the car kind of merge together, and you might see as one blurry light, right? You don't see two individual headlights when the car is really far away. But as it comes closer, you're gonna see two independent light sources, right? And what a telescope does is, the larger the telescope is, the more detail you can see. So imagine if your telescope standing here. If you have larger telescope, you're going to be able to separate those two headlights of the cars further away. With a smaller telescope, you might not be able to separate those two lights until the car gets very close to you, okay? So basically, it's a light collecting bucket. You can collect as much light as possible, more light if the telescope's larger. And also, the larger the telescope is, the more details you're able to observe. So those two are very important to astronomers in general. No matter what kind of astronomy you're doing, you want to see more details and you want to collect more light. So how powerful are today's telescopes? Okay, here is a set of Keck telescopes. This is operated by or owned by University of California. There are 10 schools in University of California, including us at UCLA. Caltech, which is the California Institute of Technology in Pasadena, and also NASA owns part of it. So we, as a part of UCLA, UC system, we are able to use these telescopes. Those are twin telescopes. Each one is 10 meters in diameter, right in there. So there's basically two telescopes that are 10 meters in diameter. And for example, what you can see is that, let's see, this is 0.3 axis. So these are not the most powerful telescopes, but for example, this Hubble Space Telescope, they're not the much, well, for Hubble Space Telescope, what you'll be able to resolve or see is that if you have two quarters side by side, right? And most of us, if you put two quarters side by side and put them pretty far away, even like 30 feet, 40 feet, 50 feet, you won't be able to see two quarters. But those telescopes will be able to see two individual quarters when quarters are put, let's say, equivalent to two, you resolving two quarters like 200 miles away. Okay, so you can see how much details we are able to see with those powerful telescopes. Okay, you can see those Keck telescopes, the ones we use regularly during the summer, they are on top of the mountain called Mauna Kea on the big island of Hawaii. So it's about 14,000 feet high. That's why you see all the clouds are below the mountains, right? And Hawaii is in the middle of the Pacific Ocean, right? So LA is right around here. Northern California is right around here. I'm hoping you can see my cursor here, right? So it's in the middle of the Pacific Ocean. And this location makes it a perfect kind of an ideal place to do astronomy because the atmosphere is very still, it's not so turbulent compared to some other places. Something about this like a little tiny piece of land in the vast, ocean. So here's Hawaii, the big islands right here. Here's Mauna Kea right here. It's 14,000 feet. It's not a big island here. You can cross the whole island in about a couple hours. So you can go from sea level to 14,000 feet very quickly. That's what it looks like. And the top, this is sort of like the mecca of astronomy or telescopes in Hawaii because it is a great site. It's the weather is good most of the time, and the atmosphere is very, it's, as I said, it's not as turbulent, which I'll get to that later on. But here are the two Keck telescopes on the right, and then this is Subaru telescope owned by Japan. It's 8-meter telescope. This is Gemini. Run by US, and here's Canada, France, Hawaii telescope. And so in lots of little telescopes around and so on. It's 14,000 feet high, so you can actually ski up there, even though it's in Hawaii, right? I mean, there's no lift or anything. So if you're gonna ski, it's a lot of work. You gotta walk up a lot with your skis or snowboard and so on, but you actually can ski or snowboard in Hawaii. So what does a 10-meter telescope look like? There is a person right here. You can see kind of the upper half of this guy in here with this hand. So that kind of tells you how large this whole structure is. But you can also see the 10-meter telescope is not one mirror, but it's like a bunch of about 36 segments put together. Okay, and this is what it is that if you have one large mirror, it's very difficult in a sense that the mirror can kind of sag or to move by its own weight. And then you need extreme precision where you're observing the light coming from, whatever the object you're looking at. And this way, with the smaller mirrors, the weight is smaller, right? Each mirror weighs less. And its own weight does not deform the mirror as easily, and you can manipulate the light more easily and so on. And then you can kind of, this works better than making the 10-meter single mirror telescope. Those are our colleagues. This is like we basically, we don't really go up to the top of the telescopes anymore. So at the bottom or in the town, nearby town, that's where the observing rooms are. Usually that's where we will go if we ever go to Hawaii, if we actually go to Hawaii, and there's observing room, and then the operators are on top of the mountain, and we communicate with each other, and they are able to kind of, move the telescope for us. And in fact, these days, we basically observe from UCLA. This picture down here is from the UCLA remote room, actually right there. From my office right now, but it's right down the hallway. There's an observing room, and basically we are connected to the telescope on Mauna Kea in Hawaii, and we don't even have to go to Hawaii. Not that we have to go to Hawaii, but we don't have to go to Hawaii to observe. And then since the COVID started, we can actually observe from our own laptop at home. So you will just wake up in like 3 in the morning or 2 in the morning and just get on the laptop and you can talk. And then actually you can move telescopes from your laptop and do the observing run from home easily at this point. Okay. So where are we going? Okay, so let me tell you something about science, because I don't want to just talk, it's almost 1 o'clock already. So I don't want to just talk about telescopes, the astronomy. So what are we trying to do with these powerful Keck telescopes? And what do we do with this telescope? And why do we need Keck telescopes to do this kind of research? And I think I already told you, but the research I've been working on last few years is to look at this supermassive black hole at the center of our Milky Way galaxy. So let me just start with the definition of what the black hole is. I'm sure most of you have heard the term black hole. It's not really an object, but it's an invisible area in space, right? Invisible volume in space where the gravity is so strong, even the light cannot get out of it. Okay? So basically, the light goes very close to the black hole. It gets basically, kind of used, we use the term, right? You might hear the term, it gets sucked in and you cannot escape, right? That's the problem. So if the light can escape, there's no light coming out of the object, it's black, you cannot see anything, right? The only reason you can see a lot of those objects in the sky, even moon, is because the sunlight reflects on the moon's surface and then we see it, right? Or stars basically, right? The nuclear fusion going on, then light is emitted from inside a star. Okay, so what does that mean if the light cannot escape? So if you think about a little physics, I'm going to give you like a 1-minute physics class, but let's say you throw a ball, right? Some of you might be able to throw it much further than some others, but if you throw it faster, it's going to go further, right? Let's say you throw it a little bit, it's going to might fall onto the ground pretty right near you. If you try to throw it really hard, it might go maybe, like 30 feet, 40 feet, 50 feet, 60 feet, and so on, right? So you can imagine, so you can so quickly think in your head, oh, when you throw harder, or when the ball is, when you throw it with faster speed, it goes further away, right? So you can, so that means if you can like throw it really fast, it'll go really fast, really much further away. And if you're able to actually really throw hard, maybe you can throw the ball from San Francisco to LA, even faster, and you can go from San Francisco to New York or to Australia. And if you do that exercise, it's obviously a thought experiment because nobody can throw the ball that fast. At some point, you're going to be able to throw it so fast that the baseball that you threw is going to go all the way around the earth and come back right behind you, right? Or even faster if you throw it, it's not going to come back to you. It's just going to go out, escape out of the earth. And that's exactly what the rockets do, right? When we have those rockets that go up the space station or beyond Mars and so on, we have to launch these rockets with pretty fast speed. It's actually 7 miles per second. So these rockets have to travel at least 7 miles every second. And when you reach that speed, you are able to get out of the Earth's gravity. Okay. Now, a black hole, by definition, is basically an object where this escape velocity, right? Escape velocity of Earth is 7 miles per second. Escape velocity is faster than the speed of light. So since nothing can go faster than speed of light in the universe, right? So if the escape velocity is faster than the speed of light or the speed of light, nothing can escape it. Even the light can escape it. It just cannot go fast enough to escape black hole. So that's what the black hole is. Okay, so I'm going to skip this. Okay. Now, how do we look for black hole? This is a tough question. There's so many people looking for black holes using very different methods and so on. Astronomers have thought for a long time that at the center of galaxies, there should be pretty massive black holes. I mean, at the center of each galaxy that you see, there should be a massive black hole right at the center. Okay. And why is that? It's the center of the galaxy. You can think of it as almost like a downtown where it's more crowded. There are more stars and the stuff around compared to the suburb of the galaxy, which is, away from the center of the galaxy. So maybe where it's really crowded, there's more mass and more likely to have some object that's like a black hole that's really dense. And then, and then maybe that's where you should be looking for a black hole. However, by definition, black holes are, you can't see them. So just by pointing a telescope in the sky, you're not going to be able to detect those things. You're not going to be able to say, oh, that's a black hole right there in my picture because there shouldn't be anything, right? You just can't take a picture of a black hole. So what do we do? So let's think about how planets go around the sun. Okay, we all know probably likely that there's sun and then there are planets going around the sun. And I think most of you know the reason that why planets go around the sun is because there's this massive sun at the center of our solar system, that all those planets want to really go a straight line, but it gets deflected, or gets kind of starting to it's pulled by the sun's gravity, and that's why it goes around. The moon is constantly being pulled by the Earth, and then that's why it goes around in orbit around the Earth. And likely Earth, Mars, all those planets are pulled by the sun's gravity, and it goes around in their orbits. So it's the gravity that makes it go around. So what do we know about gravity? We know the larger, the stronger the gravity is. Okay, so if you have small star or large star, if you go near that larger star, you're going to feel more gravity. That is, you're going to be pulled towards the larger star more likely. Also, the gravity gets larger in magnitude when you get closer to that object than further away. So if you can find a black hole, let me see what I have on the next slide. Oh, if you can find a really massive black hole, and you can observe some object really close to the black hole, right? Because the more massive it is, there's going to be more gravity from black hole. You can't see the black hole, but every object, it has the mass, so you're going to be able to detect some gravitational pull around it. So can you find some stars that are pulled by some object that you cannot see, right? That's the idea. Okay. So here's the Milky Way Galaxy. That's the galaxy we live in, the Milky Way Galaxy. And the center of a galaxy is right around here at the center. And that's where Professor Getz here at UCLA, she thought about this about 26, 27 years ago. And she thought, that's what I'm going to look for, a massive black hole. Now, you can say, all right, then let's just go to the telescope, Keck telescope, take a picture of stars around the center of our galaxy, right? And then what we're trying to find is if the stars start moving, okay? Because say, why do stars start? If you can detect the stars move around, that means there is some massive object at the center. Because if there's nothing there, stars don't go in a circle like this, just like planets won't go in a circle if there was no sun at the center of the solar system. So you can take a picture, go back to the telescope next year, take a picture again, go back to the telescope again, take a picture, and see how stars move. The problem is the stars twinkle. It makes them really nice to see at night because they're kind of twinkling, and it makes, rather than just like laser sharp lights coming from up there, but stars twinkle. But this is nightmare for astronomers because you just can't see all the stars well, right? Because everything gets blurred. So you can build the best telescopes on Earth, but as long as, well, what's making those stars twinkle? It's the atmosphere that sits on the surface of the Earth. So the starlight comes, spends like millions, billions of light years traveling towards Earth. But right at the end, it travels through the Earth's atmosphere for a split second, and it gets blurred, and that's what we observe, right? And we can't get rid of the atmosphere unless you go to space. Space telescopes are very expensive, so we can't just, you can't just build and launch space telescopes all the time. So, but you can't get rid of the atmosphere. So what do? We're kind of stuck with this, the atmosphere and blurriness of the stars' images. So what we use is what's called the adaptive optics, and those are lasers that are shot from each telescope here. And this is an actual, I did not like Photoshop like yellow lines in this photo. This is the actual photograph of when we were using lasers on top of Mauna Kea. We were on both telescopes this night. So we have two lasers. This is at the center of our Milky Way Galaxy right there. Okay, so what does this do? So let me show you this video really quickly. I won't show you the whole thing because the whole thing is very long. Let me just show you. So that's the back of the telescope where the instruments are sitting, okay? So the light comes in basically from the star or galaxy, and it gets collected by the telescope mirrors, and eventually it gets collected, goes down into the back end of the telescope where the instrument is sitting. So you can see how light is, and light gets split here, and you explain, and eventually you see the image on your computer, on your monitor as they come in. And with the atmosphere, it's gonna get blurred. It's that blurry thing you just saw. Well, what does adaptive optics do? It's basically, this mirror is a deformable mirror. So here you go. So you can see like a bunch of potato chips that comes in, right? This is basically the wavefront of the light that comes in. So now some light goes here, it gets fed into this mirror, which actually deforms in real life and corrects the blurriness of the light. That was because from the blurriness that came from the atmosphere, right, in real time. And you can see as that information gets fed in, now the light of the star you observe becomes very sharp, right? So that blurriness goes away because the deformable mirror is correcting for the atmospheric blurriness in real time. So this little video again shows you basically before the adaptive optics and after, right? Before you can see a lot of stars, but still kind of big and fat, and you can't really see a lot of details. But as you can see, once the adaptive optics is on, the number of stars, the details you can see, it's just there's no comparison between the two, like this and after adaptive optics is turned on. Okay, basically it's that the deformable mirror that corrects the blurriness of the atmosphere from the atmosphere. Okay, here's another picture. So what do you see? So if without adaptive optics, this is a picture I showed you already earlier. But with the adaptive optics, you can start seeing the detail. You don't really see anything in this box, but blown up here. And what do you see? You actually see stars going around and around and around here. Okay, and you can see this one star that's kind of going around. In fact, every star in this field of view is moving. And this is a compilation of about 10 years of data. Basically, you take the data year after year after year after year, and you take, basically you make a movie, right, of this area, the center of our galaxy. Okay. So this is before we had adaptive optics. Adaptive optics was basically on telescopes. They put it on around 2005. So again, you can see the difference between the two images, but in both cases, you see the stars moving around. And then there's, this is harder to see. But anyway, let me show you the next one. But anyway, so now you see those stars going around. You can sort of see this like elliptical way. It's going around in circular motion, just like the planets go around, okay? But you don't see anything like big, some object in the middle of the circular motion, right? If you were to see Earth going around, you see sun in the middle, and then we know that sun is the one that's pulling the Earth around the sun. Here, you don't see anything. There's just like nothing in the middle. Let me, oh, this is not the real picture. So from this data, in order for a star to go around like this, there has to be something in the middle of this orbit, okay? And seeing how fast it goes and how long it takes for one star to go around and how close it gets, you can actually figure out how much mass has to be inside that orbit, like what kind of mass there is. And then it turned out from putting the 20 years of data together, here is another video showing together. This is not the real data. This is just the simulated data. But if you follow this one yellow orbit star right here, this is called SO2. And in 2018, it came very close to the center of the galaxy. It came about like 100 AU. What is that? AU is the distance from sun to Earth. So about 120 times the distance from sun to Earth. It came that close to the center of the galaxy. And what this tells you is how much mass has to be sitting here. And there's really nothing there. Okay. And the mass of the object that sits there is 4 million solar mass. That is, the mass of the object at the center of the galaxy is 4 million times the mass of our sun. So you know our mass of our sun is pretty heavy, but it's 4 million times this mass of the sun. And you definitely do not see, if there is a star that's equivalent of 4 million times the mass of the sun, you would definitely see it, right? Because that would be quite bright, but you don't. So the conclusion is basically has to be a supermassive black hole or black hole, something that does not emit light, but definitely there's a huge amount of mass sitting there. And this is a work that Professor Gens, Andrea Ghez have done for 25 years. And this is the work that which she received the Nobel Prize last October. It was quite a day for all of us in our group when we heard the news that she got the Nobel Prize. It was very early in the morning. But anyway, but this is really her work along with quite a few collaborators. Basically, she got it for the discovery of the supermassive compact object at the center of a galaxy. And that's what you just saw. Okay, so now I have like 5 minutes. So let me see what I have. Okay, so you can see the one thing about astronomy is, so this adaptive optics, this large telescope and so on, right? So the advancement in astronomy, or how much we know about the universe, the knowledge of the universe, is closely related to the advancement in technology. It's just that we can't just, think of two separately, really. They go together. And if we don't have the technology, we can't really do astronomy. One of the questions you might have had when I talked about the blurriness of the starlight, as we observe those stars at the middle of the galaxy, or anywhere really, why don't we put the telescope in space? Here's a Hubble Space Telescope. It's still going after it was launched in 1990. So it's still going after 30 years. But anyway, it's a 2.4 meter telescope. Why do we not put a telescope in space? Then so you put it above the atmosphere. You can see the atmosphere here, this blurry whitish thingy. And then you don't have to worry about blurriness. And that's exactly why we put a telescope in space, to get out of the atmosphere, okay? I'm gonna, well, let me see. Let's turn around the question. Why do we put telescopes in space? It's not because many of us might think, well, it's because you get closer to the stars, okay? But that's not really the case. So if you think of this is a good kind of a scale to think about how big the universe is, even like our solar system. If you can shrink everything by 10 billion times, okay, so it's considered a 1 to 10 billion scale. So basically the sun will be the size of grapefruit. The grapefruit is like this big, right? It's a little bigger than your fist, maybe 2 fists put together, right? That would be the sun. And the earth would totally be the size of the ballpoint, which is basically if you have a pen, right? At the tip of the pen, there's just like a little ball that rolls around, that so you can write in the ballpoint pen. So the earth will be the size of this point, the ballpoint at the tip. And that would be 50 feet from the grapefruit, right? So imagine grapefruit here and the tip of the ballpoint pen. And then, right, they're 50 feet apart from each other, right? So first of all, space is pretty empty out there. There's not much out there. And near stars in this scale will be 2,500 miles away, which means if there's a grapefruit in San Francisco, there's another grapefruit probably in DC or New York, right? That would be the closest stars, and there's nothing much in between, okay? So that kind of gives you an idea of how big the universe is. And then just being on the top of this ballpoint on the Earth, you don't bring yourself closer to any of the stars, right? It doesn't really matter. So you're basically at the same point, whether you're on this ground, on the surface of the Earth, or above the atmosphere. So the Hubble orbit, the Hubble Space Telescope that's orbiting the Earth, it's really literally this orbit. It's microscopic compared to the entire size scale of the universe. Okay. Why do we put telescope in space? This is very important. It's a light pollution is one thing. Okay, you can see this is a map of the world. This is quite old. This was taken like almost 20 years ago. So putting the telescope, let's say, in the LA is just not a good idea because the sky, the light is basically dominated by the lights coming from the cities. So again, to get out of the light pollution, we put the telescope in space. Turbulence, we talked about as it travels through the atmosphere. Why don't we get out the atmosphere, get on top of the atmosphere, so that we don't have to deal with. Okay, is that good?
Yes.
Yes,
Okay.
excellent.
Okay.
Twinkling, we were just talking about twinkling, yes.
Let's see. I'm going to just skip to the future. Okay, so what are some of the telescopes being planned for future? Because you guys are young, so this is really for you guys. What can we, what can we hoping to discuss? This is totally incorrect grammatically, right? Um, so right, what are we trying to discover in the future? We have discovered a lot of things in astronomy, but there's plenty of things to still work on. And what are some of the telescopes that are being planned for future right now? One of the things, fascinating things about this doing astronomy is that the light has finite speed. That is, right? It takes time for light to travel from the moon to Earth. It's only like, 1.3 seconds, but it takes 1.3 seconds for light to reach Earth from the moon. So when you look at the moon, you're looking at the moon as it was 1.3 seconds ago. If you look at sun, it was like as if as it appeared 8 minutes ago. And if you do that exercise again, you see the closest star, right? It's about 4.4 light years away. So you're looking at that star about 4.4 light years away. I mean, light years, 4.4 years ago. Right? So you can think about like some of those galaxies we see in the sky in the universe are billions of light years away, 10 billion light years away, which means we're looking at the galaxy as it appeared 10 billion years ago. So the telescopes really are like time machines. Obviously we can't go backwards in time. We can't really see how universe changes because the scale, the time scale is just so long, and we are like a literally tiny blip in the entire history of the universe. So we can never really observe anything changing. But observing something that's really far away, that means you're looking at something in the past. So we can use this idea to look at how to figure out how the universe actually evolved for the last 13.7 billion years. Here's one telescope, the space telescope called James Webb Space Telescope, that is supposed to be launched later this year. It was supposed to be launched October 31st, Halloween this year, but I think it got delayed again. But basically, ideas looking at the how planets form, how galaxies formed, the first galaxy that formed in the universe, the first stars that formed in this universe, and how planets form, and right, that's sort of the questions, or the ones that are being the questions that have driven to create something like this James Webb Space Telescope. Let me just skip for the sake of time some of those things you can, right. Well, let me just go through this. So we can learn how galaxies formed. Okay, these are the bottom four pictures show how galaxies look like in today's world. These are very nearby galaxies, right? They have beautiful spiral structures and so on. The top four, these are galaxies that are like billions of light years away. So you're looking at the galaxies billions of years ago. And they don't look anything like what they look like today. So this is a kind of studies a lot of astronomers do. You basically take pictures and so on to figure out how they look like billions of years ago, and then we can figure out how they actually came out to be from this guy to this guy, right? How did they evolve? I'm going to skip that one. Here's how planets form. You can start seeing these are the little like tiny things surrounding a newborn star. Basically, this is the beginning of some sort of planetary system, right? Our solar system probably started out something like this, and eventually, is it like 8 or 9 planets formed, and then right, and then we have what we have today as a solar system. So this is something the James Webb Telescope and so on, the future telescopes are hoping to learn, to search for Earth-like planet, just not any planets around in the other planetary system, but Earth-like planet. That's really the big thing, right? Are there anybody out there? The first place you might want to think about is, well, look for Earth-like planet. Okay? If something is just like our Earth, probably likely that somebody might have eventually, some humans might have evolved on the other, this other Earth and so on. Okay, So the James Webb Space Telescope that's going to be launched later within a year, less than a year, hopefully in a few months, is 6.5 meters in diameter compared to Hubble Space Telescope, which is 2.4 meters in diameter. So it's much bigger. It's a technological, it's a wonder, because this, you can't just launch something like this in the rocket. So it's like an umbrella that folds in, and then when it goes up in space, it folds out. This whole yellow part, the mirror, folds out in space. And hopefully it will work, because we can't send astronauts like Hubble Space Telescope to fix anything anymore. It's out there and that's it. That's a picture of Hubble Space, James Webb Telescope. You can see how big it is again. It's sitting down in Southern California right now, I believe. That's where they're building it. It's pretty much done right now, just waiting for the final checks and so on. And then hopefully it will be launched very soon. This is a 30-meter telescope that University of California is trying to build. And I don't have time, sorry. I'm like rushing through so many things. But basically, as the name indicates, because it doesn't really have a real name yet, it is going to be 30 meters across, okay? So just to show you, here's a 10-meter Keck telescope, and you saw how big it was compared to that person that was standing right in front of the mirror, the 10-meter mirror, the telescope. Now it's going to be 30 meters across, 3 times across, bigger. And then, so what that means is the mirror is pretty much going to be as big as the infield, the baseball field, right? So it's enormous. It's an enormous structure, enormous thing that we're trying to build. And there are a few of these in that are being planned around the world right now by Europeans, another group in US, and so on.
We are definitely into your Q&A time right now.
Yes,
So,
okay, I'm gonna finish, so that's it. I'm gonna just finish right here.
so I think what's interesting here is today is Technology Tuesday, right? So, and a lot of people think of technology as computers. Technology is using tools to make sense of the world around us. And that's what is happening here. We need to, as you said, marry the science, the astronomy to the technology. The two have to go hand in hand in order for us to investigate it more. So I'm going to open the chat box here, and we're going to see what kinds of questions we have to answer. We're probably only going to be able to take a couple questions at this point, because we need to, I want the girls to really have a conversation among themselves about reaching for the stars and what causes stars to twinkle. I mean, we talked a little bit about that, right?
Yeah, it's the atmosphere basically that makes it blurry. I saw some question up there.
Sorry, go ahead.
No, should I just go ahead and answer? Well, there are a gazillion things here.
No, I've been seeing Holly with her hand up for a long time, so I was thinking of calling on her.
Well,
Yeah,
let's
sure.
give her a chance to look through just the questions, so we see what's the questions, and then we can ask the question. Just give her.
But go ahead and ask questions.
Okay. Do you want to stop sharing so we can look at just you?
Oh, sorry.
There we go.
All right. Okay. All right. Yeah, go ahead with questions. I know many of you have hands up.
Holly?
Yeah, mine's just a quick question, but I had to keep my hand up, and otherwise I would have forgotten it. You know how you said black holes are invisible? Didn't NASA like get a picture of one recently, like a few years ago? How'd that work?
So yeah, so the donut thing, right? The donut shade picture that you've seen. Yeah, so that was basically how light is, so as the light goes near the black hole, usually kind of spirals in, and then someone gets reflected back, or just it comes around and it gets, deflected, and eventually gets, observed by us. And that's the picture you saw. So you didn't really, so the reason it was donut shaped was because right in the middle, that's where the black hole is. So anything that came within that radius was basically sucked in, and nothing could get out of it. So what you were seeing was the light around the black hole, and as they are traveling around the black hole.
Wow.
Yeah.
Cool.
Did that
Okay.
answer?
Bella.
What fascinates you the most about studying astrology that you study?
Astronomy. What fascinates me? Lot of things. Um, Gosh, that's a really good question. I should have thought about it before. Um, One thing about astronomy, so there's definitely a technology part too, but I didn't get into it at all. I didn't have time. But one of the reasons I really got into astronomy, a lot of us just look up the sky and go, oh my gosh, look at that. There's like millions of stars. If you go to the very dark side, or you go to the planetarium and it gets fascinated by what those planets are doing or the stars are doing. But the other thing I was really fascinated by, it was that when I started studying math a lot, and in high school, when I was introduced to physics, I was really fascinated by like the fact that you can describe things with math, the things in the universe, you can actually use mathematical equations to describe. And that kind of fascinated me.
Uh-huh.
And then astronomy really is physics. It's applied physics. So we do basically, it's all mathematical and physics, really doing physics, just applying to stuff in the universe. So up in the sky. So that was how I kind of got into astronomy, not just like, like it looks pretty, but the fact that the physics is used to describe objects, how they move, how they shine, it's all kind of the physics is related. So the physical science part. But right now, what fascinates me, I don't know, a lot of things. I mean, this is like a black hole thing. It still fascinates me. There are a lot of things we're finding out right around the black hole, not just like how big the black hole is and so on. But it turns out there are a lot of young stars are being born around the black hole, and we don't know why, because the theory says you should not see young stars around it. We're missing a lot of old stars around the black hole. We shouldn't be missing a lot of black holes. So it's like there are a lot of questions that we still get as we observe more and more. We keep going with the observation of those the galactic center area. So there's no really one question. Sorry, I'm just going in circles, but there's really no one answer.
So Jocelyn.
Hi, I wanted to know if the Andromeda Nebula, is that like a group of stars or is it like another part of a galaxy?
And Andromeda Nebula is within our galaxy. It's
Okay.
basically where like a gas, there's like a lot of gas around there, and then the stars shine on the gas and it emits, light. And then that's why it kind of looks nice. It looks really, it's not a star or planet. It's really like the big chunk of gas that's right around there.
We're going to
Okay,
take
thank
a
you.
couple more questions. So Rebecca.
How do stars collapse on themselves? Like, how do they just go away?
Good question. The reason is because it just gets so much stuff gets like a black hole basically collapses on itself. That's what happens. What happens is basically okay. So why doesn't the sun collapse? It's because actually there is a lot of stuff being born or the material being produced at the center of our sun. It's called nuclear fusion. It's a little bit that provides kind of outward pressure. So the gravity tends to put things together, right? Pulls everything together. But the nuclear fusion that's going on at the center of the star brings everything outward. So those two things get balanced, and so that most stars don't collapse. But once stars get old, they just don't have any more stuff to burn. I mean, you can think of it as like fireplace running out of the logs, and it just stops burning.
Mm-hmm.
And that's going to happen to most stars. And eventually, what happens is it cannot keep producing energy, this outward energy. So the only thing left is gravity that's just going to pull everything together, and it's just going to collapse into itself. And just
so at this point, I'm going to put the girls into their breakout rooms, and I'm going to invite you to go from breakout room to breakout room. We have 10 breakout rooms, and you can maybe stop in at each of them and see what they're talking about, because this is time for them to have a discussion about what we just were talking about and the possibilities that might be out there for them.
And Miss Shoko, if you could, I think a few girls asked for your email to ask questions.
Oh yeah.
So if you could provide your email.
Right here.
Why don't we provide the information for all of the speakers afterwards, Alexis, for
Okay.
all of them? Okay, so say
Okay.
that. We'll just do that for everybody.
Okay.
Okay, so I am basically going to give the breakout rooms about 15 minutes, 20 minutes to talk about what we were talking about and to take attendance for the afternoon session. And then we'll come back into the main room for the first workshop of the afternoon, the first required workshop, which means that all of you who participated in the inspiration hour for the afternoon session should stay on, campers and workshop coaches. So do not leave after the breakout. Thank you. Okay, I'm going to open the rooms and we'll see what happens.